Welcome, students. So what I'm going to do now is try to make a video to go over our next section, which is 10.2, and introduce polar coordinates. And this is on page 721. So in introducing polar coordinates, I'd like to begin by just having us reconsider for a moment our normal graphing system. So let's say we have our x-axis and we have our y-axis. So when you have a point in our normal graphing system, like let's say I have a point here, 1, 2, 3, 4. This is over where x is at 5 and y is at 3. And so we have coordinates of a point, and we give the coordinates as being 5, 3. Then the idea is that the x value shows the position of the point in the left to right direction, and the y value shows the position of the point in the up and down direction. And that using the x position and the y position, I can uniquely identify any point on the graphing plane. And so once I've told you the x and y values, you know where the point is. If you had to find the point, you would go so where x is equal to 5. So for example, if I look along this vertical line, these are all the points where x is equal to 5. And so since x is 5 and the point that we want, we know it's somewhere on that line. And similarly, I would go to all the points where y is equal to 3, which is that horizontal line. And then the point where x is 5 and y is 3 is where those intersect. And that's why graph paper has these up and down and side to side lines on them, horizontal and vertical lines, because each line represents a consistent value for one of the variables, and it makes it easier to go to a specified point, like in this case where x is 5 and y is 3. So now let's consider looking at a point a different way. So let's say I have some point on my graphing system here. And in this case, I can see x is 3 and y is 5. But what if I was considering the angle of inclination to the point? So let me draw sort of a ray here. And you were sort of thinking like when you did with trigonometry, that at any point on a unit circle has a theta value representing the angle that you would have to turn away from the x-axis until you are facing straight at that point. And then if this were a point on a circle, for example, there would be some radial distance from the center, the origin in this case, to that point. So let's say this distance is r. In this case, we could actually figure out what r is because we know what this point is. R would be equal to, well, since the height is 5 and the base is 3, it would be the square root of a squared plus b squared, which would be like what? Square root of 24? It's 34, something like that. In any event. So imagine that we have a point here, and that instead of identifying the point by saying what its x position and its y position is, we're going to identify the point by telling somebody, I tried to erase there, by telling somebody how far they have to turn to face toward the point, an angle of inclination, and then what distance they need to travel to go to arrive at that point. And then they could say, all right, turn up to this particular angle, then travel the needed distance and stop, and then you'll be on the point. So this, when you give those two bits of information, so you could you could provide theta and r instead of x and y to identify a point. So if you do that, then you have a different kind of coordinate system. So x and y values are called the Cartesian coordinate system. When you give theta and r the angle of inclination from what would be the x-axis and the radial distance or the distance from the origin you have to follow at that angle to get to the point. When you give those values, that's called polar coordinates. So with polar coordinates, you're giving a theta value and you're giving an r value. And typically, for whatever reason, they have the r come first and then the theta, probably because it's alphabetical, like x and y. And so you identify a point by giving how far away it is from the origin, which is the r value, and the angle that you need to turn to face toward to head toward the point. And that's called polar coordinates. Instead of Cartesian coordinates. So this still identifies a point. You can say, okay, I have some point over here, putting this in the third quadrant. And so to get to that point, maybe I'll switch to yellow here, I would need to imagine that there's a ray from the origin through that point, and I would need to identify the angle of rotation, theta, to get to that particular ray, and I would need to identify the length r, or the radial distance that that point is away from the origin, and then that would lead to giving coordinates r and theta to identify this particular point. Okay, so having said that, let's look at some specific examples. And so the first thing to do to warm up to the idea of polar coordinates is to simply imagine that given a pair of polar coordinates, you could find the point that they refer to. Or on the other hand, if you knew of a particular point and you wanted to identify it, that you could use polar coordinates to do so. And we will often in the beginning go back and forth between the point being communicated in Cartesian coordinates with x and y, and then polar coordinates with r and theta. So that translates into wanting to take a point in Cartesian coordinates and converting it to polar, and being able to go backward, given a point in polar, being able to convert that back to Cartesian. If you can go back and forth between the two, then you're able to use either. So let's maybe scroll down here a little bit and look at sort of a couple of simple examples. So I could say something like, give polar coordinates for the point 4, 4. Where 4, 4 is the Cartesian coordinates of the point. So we can imagine that I have a graphing system. Let's try to do this nicely. I have a graphing system like here. There we go. And so I can identify the point just so that we're all clear that it's 4, 4 is 4 to the right, and up 4 would be right there on my graph. So there's the point 4, 4. And then I can think about how would I translate that. I think that's 5, 4, isn't it? Let's get the right point. 4 to the right of 4. There we go. So then what I want to do is I want to imagine expressing this distance r and this distance theta for that, I'm sorry, not that distance, that angle theta, so that that's the point that you would have. Well, since this is I can imagine quickly a little triangle here where the height is 4 and the base is 4, then by the Pythagorean theorem, I know the r value is equal to the square root of x squared plus y squared. So in this case, I would get 2 root 2. I'm sorry, 2 root. root 2 times, yeah. So let me write that out. So that's the square root of 32. And there's a 16 in there, so that becomes 4 times the square root of 2. So that's the r value. Now the theta value, again, we could use triangles and think about opposite over adjacent. So that would tell me that I would want the inverse tangent of the opposite over adjacent, the sides, because I know the tangent is equal to opposite over adjacent, which is 4 over 4, or 1. So if I take the inverse tangent of that, I should get the angle. And that's going to come out to be pi over 4. We can, of course, see it in this case, and we know that pi over 4 is a 45-degree angle diagonal, or the line y equals x. But nonetheless, you could just simply stick the y divided by the x value of the point put into the inverse tangent to come up with the angle. So this case, we then get that the r theta that I wanted was that r is a value of 4 times the square root of 2, and the angle was pi over 4. So here's an example where, given a point in Cartesian coordinates, we were able to convert that to the way to express that in polar coordinates. Okay, so now let's maybe clear this page and then look at an example the other way. So now let's say instead that, actually I think I can get my graph back, one sec. Let's go back here and then let's just clear the, no, sorry. Not what I wanted to do. I thought I could just clear the ink here. Give me one sec. Clear ink, there it is. Just got to see it. Okay, so then I have my two little grids here still. All right, so now we just went from Cartesian to polar. So now let's say instead that we wanted to go from polar coordinates into Cartesian coordinates. And so we would have an r and a theta. So maybe let's say I had 3, and I'll do something nice like 3 pi over 2. So again, in polar, you're looking at an r and a theta, whereas to get that into Cartesian coordinates, you want to express that in terms of an x and a y. And it's very good in the beginning to kind of try to visualize these things, I think. So imagine that I would just try to plot this point by given r and theta. And usually you'll actually use the theta value first. So if I'm circling around from the x-axis, then as I open up my angle, I get to pi over 2, pi, and 3 pi over 2. So 3 pi over 2 as an angle is the line basically pointing straight down from the origin, or the negative part of the y-axis, if you want to think about it that way. So that's my theta. And then along in that direction, I want to go down 3. So I move 3 spaces down, and I end up right here. Because I went down 3 spaces for my distance, and my angle, theta, was equal to 3 pi over 2. Okay, so there's the point. Now, of course, we could just see that, now that we see that point. So the point that's here is on the y-axis, so the x value is 0, and the y value is minus 3. So what we did is, in this case, we sort of oriented ourselves in the direction of the theta. So this is direction that you're going to then travel the needed r length. And then this is the distance you move in that direction, in the theta direction. And then in this case, once I was pointed down, as I need to be for angle of 3 pi over 2, we went down 3 to get the r value, to have the r value translate into the point. So there's an example of going from a point given in polar coordinates and seeing what that would be. Now, you can also imagine that if I have, in general, some particular point, and I have an r value and I have a theta, that if I wanted to know the x value of that point, well, we can think of it back from our trig, that the x value is the value to the left and the right, and that we can use a cosine for the x value. So we know that according to standard trig, the x value is equal to the radial length of the circle you're using times the cosine of the angle. And the y value, similarly, is equal to the radial length of the circle the point is on times the sine of the angle. And so we could have looked at that this way, so that in this case, if I had done that, this would have been 3 times cosine of 3 pi over 2. And cosine of 3 pi, so cosine of 3 pi over 2 is 0, so this would have given us 0. And similarly, the y value would be 3 times sine of 3 pi over 2. And sine of 3 pi over 2 is -1, so that would be -3, and that's sort of formulaically how we could have gotten these 2 points. I'm sorry, 2 coordinates. So here's an example of going from polar to Cartesian coordinates. And so let me sort of sum this up of converting from one to the other real quick. And so in general, if you're going from polar coordinates to Cartesian coordinates, then x and y formulaically can be found by taking r times cosine theta and r times sine theta. And if you're going from Cartesian coordinates into polar coordinates, then the r value is going to be equal to the square root of x squared plus y squared, as we saw earlier, by using the Pythagorean Theorem. So you know x and y because you're given the Cartesian coordinates points. So you plug them in here to figure out r. And that theta is the inverse tangent of the y value over the x value, opposite over adjacent. So these are formulas that you can sort of use directly. We kind of looked at why this makes sense from our first couple of examples, but hopefully now these formulas make sense as well. So that's our introduction to start with the idea of being able to express a point in now one of two ways: our standard xy coordinates in Cartesian coordinates, and then a possible way that's different is in polar coordinates, where you talk about the angle you turn toward to look toward the point, and you give an r value for how far you would walk in that direction to land on the point. So what I'm going to do is stop this video now just to make it a little bit more manageable in length, but we still have a lot more to do, and I'll make another video to pick up from where we left off here.